Ever find yourself staring at a simple math problem and, it's like, whoa, there's actually a whole lot more going on here than I thought. That's kind of what today's deep dive is all about. We're taking a chapter titled Playing with Numbers, and trust me, it's way more interesting than it sounds. Get ready to unlock this hidden world of factors and multiples.
You know, it's funny how these really basic math concepts, they're like the foundation for so many other more complex mathematical ideas.
Totally. It's like that saying, sometimes the smallest things have the biggest impact. And this textbook jumps right in with a great example, arranging 6 marbles.
You can arrange them in a bunch of different ways, right? Like you could have 1 row of 6 marbles, 2 rows of 3, 6 rows of 1. Each one of those is like a visual representation of the factors of 6.
It's like a little puzzle, figuring out all the ways to fit those marbles in there nice and neat.
Exactly. And that's a perfect illustration of what a factor is. It's any number that divides evenly into another number. So 1, 2, 3, and 6 itself are all factors of 6.
Okay, and this is where it gets kind of cool. Have you ever heard of perfect numbers?
Yeah, 6 is actually the smallest perfect number. If you add up all of its factors, 1, 2, 3, and 6, you get 12, which is double the original number.
Wow, it's like this hidden harmony.
Yeah.
Right. The textbook also mentions 28. 1 plus 2 is 3, plus 4 is 7, plus 7 is 14, plus 14 is 28. Plus 14 is 28, and then plus 28 is 56. See? It works.
Mathematicians love these perfect numbers. They've been studying them for centuries. They're not that common, and some mathematicians think they might have other hidden properties. We just haven't discovered them yet.
Okay, so let's move on to multiples. I always think of building blocks like Legos. The textbook shows these strips that are each 3 units long, so 1 strip is 3, 2 is 6, 3 is 9, and so on.
Yeah, you got it. Multiples are what you get when you multiply a whole number by other whole numbers. And it relates back to factors because a number is a multiple of all of its factors.
It's like factors and multiples are 2 sides of the same coin. All right, let's talk prime numbers. The independent spirits of the number world, only divisible by 1 and themselves. What are some prime numbers that come to mind?
I think of a prime number as like that fundamental building block we were talking about. You can't break it down any further. And something that's important to remember is that the number 1, it's not considered prime or composite.
Right, it's in a category of its own. So the textbook mentions this method for finding prime numbers called the sieve of Eratosthenes. It's like a number puzzle. You sift out all the composite numbers until you're left with only the primes.
It's actually pretty simple. You start with a grid of numbers from 1 to 100. You circle the first prime number 2, and then you cross out all the multiples of 2.
So you're basically getting rid of all the even numbers right off the bat.
Exactly. Then you move to the next number that's not crossed out, which would be 3. Circle it, and then cross out all the multiples of 3. Keep repeating that process.
And you end up with this grid of circled numbers, and those are your primes.
It's cool to see how it creates this visual pattern of how prime numbers are spread out.
It is. Let's take a quick detour to a more familiar concept even, and odd numbers. It all comes down to whether a number is divisible by 2. Even numbers, always willing to share odd numbers they like to keep to themselves.
And a fun fact about that is that 2 is actually the only even prime number. All the other prime numbers are odd.
2 is a special number for sure.
Okay.
Let's talk shortcuts divisibility rules.
Yeah.
It's like having a cheat code to know if a number is divisible by another number. You don't even have to do the whole division process.
Yeah, it's all about recognizing patterns. Like for a number to be divisible by 2, the last digit has to be even. 0, 2, 4, 6, or 8.
A classic. And I love the one for 3, you add up all the digits in the number. If that sum is divisible by 3, then the original number is 2. Like 54, 5 plus 4 is 9. 9 is divisible by 3, so 54 is 2.
You got it. And another easy one is the rule for 4. If the last 2 digits of a number are divisible by 4, the whole number is like 116. 16 is divisible by 4, so 116 has to be as well.
These rules are so convenient.
Absolutely. They can save you a lot of time and effort.
Now for prime factorization. It's like taking a number and breaking it down into these tiny little prime building blocks. The textbook uses the example of 24. No matter how you break it down, you always end up with 2 times 2 times 2 times 3.
Each number has its own unique prime factorization. It's like a fingerprint for that number.
This is amazing.
Yeah.
I'm starting to see numbers in a whole new light. Before we jump into even more mind-blowing applications of factors and multiples, let's take a moment to digest all this incredible information. Are you ready to dive back in?
Ready for more?
Oh yeah, I'm hooked. We're about to unravel the mysteries of HCF and LCM. It's like they're the dynamic duo of the math world.
I like that. So HCF stands for highest common factor. Sometimes it's called the greatest common divisor. It's all about finding the biggest number that divides perfectly into 2 or more numbers.
Gotcha.
LCM is lowest common multiple. And that's about finding the smallest number that's a multiple of a group of numbers.
So it's like if we go back to those Legos, HCF is finding the biggest brick they all share, and LCM is figuring out the smallest base you could build with them.
That's a great analogy. And actually, the textbook gives us some pretty cool real-world examples.
Like that kerosene problem. We've got these two tankers. One's got 850 liters. The other one has 680 liters. And the question is, what's the biggest container we could use to measure out the kerosene from both of those tankers and get an exact amount with no kerosene left over?
That's where HCF comes in handy. The biggest container size that would work in that case is 170 liters.
No kerosene wasted. That's awesome.
Oh.
I love how this all connects to real life. Oh, and what about that example with the morning walk?
Which one?
You know the one where those three people start walking together? But they all had different strides, 80 centimeters, 85 centimeters, and 90 centimeters.
Yeah.
How far do they have to walk before they all line up again?
That's an LCM problem. We need to find that sweet spot where their steps all sync up.
Hmm.
And it turns out they'd have to walk 12,240 centimeters.
Wow, that's a long walk. But at least they'd be in sync. That reminds me of another example from the textbook, the traffic light problem.
Classic.
So there are these three traffic lights, and they all change at different times, 48 seconds, 72 seconds, and 108 seconds. They all change at the same time at 7 a.m. When will they be in sync again?
We've got another LCM situation on our hands. The smallest common multiple of those three intervals is 432.
Which translates to...
7 minutes and 12 seconds.
So it's 7.07 in 12 seconds. Those lights are going to line up perfectly.
Mark your calendars.
I'm starting to see HCF and LCM everywhere now.
They really are everywhere.
It's like they're the unsung heroes of the math world.
And they have some seriously important applications. Remember those prime numbers we were talking about?
Yeah.
They're essential for online security and cryptography.
Wait, really?
Yep.
My online shopping is protected by prime numbers.
Exactly. Because prime factorization is really, really difficult to reverse, especially with really large numbers. So it's the basis for a lot of our online security measures.
Wow, that is so cool. I had no idea. This deep dive just keeps getting better and better. Prime numbers protecting my online shopping. Who knew?
It's all connected.
It really is.
And we're just scratching the surface here. There's a whole universe of mathematics out there just waiting to be explored.
Okay, so we've talked about factors, multiples, prime numbers, HCF, LCM. What else is there?
Well, have you ever heard of twin primes?
Oh, twin primes.
Yeah, tell me more. So imagine these pairs of prime numbers that are only two numbers apart, like 3 and 5 or 11 and 13. They're like close siblings in this vast sea of numbers.
Like that.
And we found some really, really big twin primes.
Really? How big are we talking?
Huge.
Wow.
But mathematicians still haven't figured out if there are an infinite number of twin primes.
That's a really good question. Infinite twin primes, huh? It's like a never-ending scavenger hunt for mathematicians.
It really shows you how much we still don't know about numbers. And speaking of things we don't know, did you know that we're still discovering new prime numbers today?
Wait, what? I thought we had all the prime numbers figured out by now. I mean, they seem so basic. How are we just now finding new ones?
Well, it's like this. The bigger the numbers get, the harder it is to find prime numbers. We need these super complicated algorithms and powerful computers to find them.
So it's like trying to find a needle in a haystack.
Yeah.
But the haystack is the size of the universe.
Exactly. Every new prime number we find, it's like adding another piece to this giant puzzle. It helps us understand these fundamental building blocks of math.
I'm kind of blown away by this whole idea. Prime numbers going on forever and us still finding new ones. It's like the world of numbers is always expanding.
It really makes you think, doesn't it? Even in a subject like math, where everything seems so certain, there's always more to learn, always new mysteries to solve.
It's actually pretty inspiring. It reminds you that learning never really ends.
It's a lifelong journey for sure. And sometimes the biggest breakthroughs come from looking at familiar things in a new way. It's so true. Who would have thought that factors and multiples could be so fascinating? We started with arranging marbles, and now we're talking about cryptography and the infinite nature of numbers.
And we've just scratched the surface. There are so many more amazing mathematical concepts out there, just waiting for us to explore them.
Well, I think we've given our listeners a lot to chew on today.
I hope so. If there's one thing I want listeners to take away from this, it's that sense of wonder and curiosity about numbers.
Yeah, because even in the simplest math concepts, like the ones we talked about today, there's this whole universe of beauty and complexity and endless possibilities just waiting to be discovered. Thanks for coming on this amazing journey with us. Until next time, keep those minds curious and those calculators handy.